Hello everyone, welcome to today's session. I'm so excited to start our final module together, where we pull everything we've learned so far into a cohesive picture of system architecture. Today, we are kicking off Module 4, which is all about communication and back-end patterns. This is where the real magic happens in distributed systems. As this subtitle suggests, we'll be exploring the backbone of service-to-service interactions. In a world of microservices, no service is an island. They must communicate efficiently to deliver value. We'll start with an overview of distributed systems and identify the specific challenges like latency and partial failures that arise when services talk to each other. Our roadmap today is comprehensive. We'll compare REST and gRPC, dive into message queues, and look at strategies like rate limiting to keep our systems healthy. This visual here illustrates the complex web of connections we'll be mastering. By the end of this module, you'll know exactly which pattern to choose for any given scenario. Let's dive in. Building on that overview, let's dive into our first major pattern: REST APIs. REST stands for Representational State Transfer, and it has become the gold standard for how web services communicate. At its core, REST relies on standard HTTP methods that you're likely already familiar with: GET to retrieve data, POST to create it, and PUT or delete for updates and removals. It's a very intuitive way to interact with data. A key concept here is statelessness. This means that the server doesn't store any session data about the client. Every single request must contain all the information needed to be processed, which makes these systems highly scalable. We also treat everything as a resource identified by a URI, and we almost always use JSON as our data format. It's lightweight, flexible, and extremely easy for us to read and debug. Now, let's look at how this actually flows in practice. Notice in this interaction how the client and server are decoupled. The client sends a request to a specific URI, and the server responds with the data. This separation allows the front-end and back-end teams to work independently, which is a massive advantage in modern development. Keep this flow in mind, because we're about to see how gRPC handles things quite differently. Building on the REST concepts we just covered, let's look at a different approach. While REST is the industry standard for public web APIs, gRPC is the high-performance powerhouse often used under the hood in complex systems. The secret to its speed lies in its foundation, HTTP 2. Unlike the HTTP 1.1 protocol that most REST APIs use, HTTP 2 supports multiplexing. This means we can send multiple requests and responses at the same time over a single connection, which drastically reduces latency and overhead. Another major shift is how the data is formatted. Instead of using JSON, which is text-based and easy for us to read, but relatively heavy for machines, gRPC uses protocol buffers, or protobuf. It's a binary serialization format, which makes the messages much smaller and much faster to process. As you can see in this comparison, the efficiency gain is significant. This is why gRPC is the ideal choice for internal service-to-service calls, what we call east-west traffic, where performance is the top priority. It also uses strongly typed contracts through proto files, so there's never any doubt about what data is being sent. So, we have REST for the public web and gRPC for internal speed. Next, let's put them side by side to see exactly when you should choose one over the other. Building on what we just covered, let's put these two protocols side by side. Choosing between REST and gRPC isn't about which one is better overall, but about which one is the right tool for your specific architecture. Looking at this comparison table, the fundamental shift is in how data is packaged and moved. REST uses JSON, which is human-readable and great for debugging, while gRPC uses protobuf, a binary format that is significantly faster and smaller, though harder for us to read directly. Also, notice the transport layer. While REST is generally tied to HTTP 1.1, gRPC requires HTTP 2. This gives gRPC built-in advantages like multiplexing and bidirectional streaming right out of the box. So, when do you stick with REST? It remains the gold standard for public APIs and web-based clients. Since every browser understands REST and JSON, it's the most friendly choice for external developers who need to consume your services. However, for your internal microservices, the engine room of your application gRPC is the powerhouse. It's ideal for low-latency communication and polyglot environments where you have services written in different languages that need to talk to each other as fast as possible. In short, use REST for the public front door and gRPC for the high-speed internal corridors. Building on what we just covered regarding API protocols, it's time to talk about the rhythm of how these messages are sent. In back-end engineering, understanding the difference between synchronous and asynchronous communication is absolutely vital. First, let's look at synchronous, or sync communication. In this model, the client sends a request and then waits, literally blocking any further action until the server finishes its work and sends a response back. Think of it like a phone call, You can't really do anything else while you're waiting for the person on the other end to answer and give you the information you need. Now, contrast that with asynchronous communication. Here, the client sends a message and moves on to its next task immediately. The processing happens in the background. A perfect real-world analogy is sending an email. You hit send, and then you're free to do other work. You don't just stare at the screen waiting for a reply. The response comes whenever it's ready. If you look at this diagram, you can see the clear difference in the blocking time. In the sync flow, that gap where the client is doing nothing but waiting can become a major bottleneck if the server is slow. Ultimately, moving to asynchronous patterns where possible can drastically improve the user experience because the UI doesn't freeze. It also ensures system resilience, allowing us to handle heavy tasks without crashing the main application flow. Does that distinction make sense to everyone before we see it in action?